recording option so that you can have a copy of this later. Uh, so once more, good morning. Let's start. I'll straight jump into flow simulation here so that we can quickly see the capabilities of it. Okay. Let's look at flow simulation. Okay. There are many things which we discuss about flow, but one of the basic topics which I highlight and which one can easily correlate is on the fact that one can visualize it inside flow simulation or CFD software for that matter. Honestly, fluids and gases are such a thing which can be visualized easily unless they do some special experimentation, like having a certain gas inside a certain gas or a colorful liquid inside liquid to see how it is moving. Otherwise, it is almost impossible to visualize a liquid the way it behaves internally. Only a software or only a virtual front end can give some idea on how a liquid might be behaving inside a given domain. That this is a broader perspective, but specifically we do have many different things, like we are talking about understanding pressures, understanding velocities, understanding temperature variations, density variations, and the forces that a liquid or a gas puts on a or a solid geometry. So these can be understood using flow simulation, that is, or CFD software, and these are a few different things which even our software does. So let's move on. Let's quickly, for the 4 minutes, get a good feel of different capabilities of flow simulation and use this product capability slides itself to understand and explain it. First, as simple as internal flow analysis. So here it could be, we understand, a typical given domain coming in from a certain input and fluid is going out from another exit. So create this closed domain and software calculate for us the behavior of the fluid inside this domain. One basic thing when we do it, typically we want to understand again the pressures, the velocities, the liquid is going to exert itself on the structure. If at all temperatures are there, then the behavior of those temperatures. We also call this as an internal flow liquid. Sorry, analysis. The second part could be an external flow, where a liquid is flowing something like this on, that is, it could be atmospheric condition, or I mean to say in an open environment condition, and a liquid or gas is flowing on this object. You are saying this to be an external flow condition. Ultimately, it will have its closed boundaries, and it is thought that anything after these boundaries is infinite area, and we analyze, or the calculations are done within this closed domain. This is how it goes on. That part of that kind of analysis can also be done for external use flow simulation. Now, applications, it could be more aerodynamics, understanding the forces that the external environment is going to bring on the structure. It could also be for simulating appropriate heat dissipation. So all these things can be done using this external flow. There is a which I have added here, a dynamic analysis or understanding the behavior of the fluid at different angle of attack. Now take this example. The pressure plots are being shown here. We are seeing the behavior of those plots on the structure at different angles. You can see when the vehicle is moving at different angles, it depends. Like, unfortunately, there is no animation for this. It is more of multiple slides. So I am in a row. You can slowly move through it. It appears as though the animation is happening and the object is actually moving in that direction. But at this stage, you can see a certain amount of recirculation that is happening here, which is not desirable and can lead to negative pressures, and it can topple as well. So those kind of behaviors as well, if you see it in specific values, then the comparison chart has been given here, where you're seeing the drag force, the maximum temperature, and the total drag. So probably if I compare only one of it, which is the total drag, you can see here it goes on increasing as the angle of attack goes on. Obviously, this is very high and may not be desirable here, etc. Around, if I compare probably the temperature, yes, the temperature is going down when the angle of attack is high. Obviously, more surface area is exposed to a different or a higher velocity, and that can make a difference. But kind of graph can help an user design a aerodynamic vehicle or a flying object. Applications like signboards, it's like buildings, wind turbines, big buildings. All those can be understood and analyzed using the flow analysis. Now let's see the second capability, which is more on heat transfer. So here the that temperatures come into picture. So liquids, pressures, density, all those remain. And from that, one more degree of freedom which is sought is temperature. And typically or conventionally, one of the important is called as conjugate heat transfer, wherein the heat is dissipating or moving from a solid component to liquid component. So typically this kind of analysis is called as an conjugate analysis. And the way it works here, you can see the air is expected, or we are using air to dissipate the heat from two different points. Would be somewhere this particular capacitor which is producing the heat. This heat is taking to the heat sinks or heat exchanger somewhere around here, and the fan is going to blow out that heat from the heat sinks out that atmosphere. So I want to design where to have these holes, the fans, etc. All these kind of details of the location of fans, inputs, outputs can be designed over here. Let me check it. And the part of the application could be in terms of heat exchanger, where it wants to understand how much heat is dissipated from one liquid to the other way around. So those details can also be understood using this kind of analysis. I wish I could for this to move from a pen to this. Anyways, let's go back. Component. So one was the temperature. So one was as simple as liquid flow, second temperature, and one is rotating component. Now with 2015, you might be knowing we have two different options for rotating components. Previously we had only the sliding mesh. We can have one more option now in 2015, by which we can actually simulate unsymmetric flows. That is, previously we were required to have a flow where liquid came absolutely vertical to the axis or parallel to the axis of the turbine or the blade, and it should go tangentially, or I would say in the horizontal direction. If it's a flat direction, then it should go. So if I try to show you a text or a pen here, so the requirement was fluid should come like this, and either it should go like this, or where from here, how really outside, other as well. So that was a big limitation in the past, but could simulate only certain kind of pumps or turbines. But we have one more step wherein we can use a sliding mesh, and limitation is no existing, and we can actually simulate things as those shown on the screen. Especially this one, you can see here the turbine is not actually a cylindrical turbine, and we can actually, the liquid can move, the liquid can be asymmetric to the flow of the direction. There could be other applications like a lobe pump, or impeller, which how can I think I need to an image of that. So those kind of different things wherein the fluid may be coming in a kind of fluid and air mixture, or spray of a fluid is being put on a turbine, etc. So unfortunately, those scenarios we cannot simulate in the software even today. So try to understand this is a very good, strong feature. It will actually give very nice and accurate results. It has some limitations which needs to be acknowledged, understood, and used appropriately. I can see a few questions coming up. So then, can we use sliding mesh to evaluate a flexible impeller pump? I know what this means. Flexible impeller pump. Let me make it so that if I get an image, it would be easy to discuss. Guys, please ask. Let's take the opportunity to give the session. Flexible impeller. Yes, I think. Oh, David is asking, but yesterday someone from Indonesia had a similar question. So something like this. What happens is, can I have a pen? In this case, the impeller blade size is changing. Okay, impeller blade size is changing. And unfortunately, we cannot do. So to understand this, the structural domain or the digital details of the structural domain remain the same. Only thing which changes is the way the fluid is going to flow, and that is acceptable. So unfortunately, that cannot be done. It needs a technology called as mesh morphing, where mesh changes its volume over time as per the requirement, and that can be done. And just to show you, even this particular kind of pump, which is more of a gear pump, uh, gear thing like this, with an animation. I didn't want an animation. Yeah, so like this, two different domains are two different poles mixing into each other. Unfortunately, even those do not be simulated in our software at the moment. Okay, I think let me check. I need some more images to, or else I have to open in. Let me open that email itself. So if you see over here, end of pump cannot be simulated in our software, wherein you have pump, a impeller is blowing the probably steam or a liquid on this small such. Unfortunately, even those cannot be simulated in our software. Question, guys. So one final thing which is relevant in terms of broader level application of flow simulation is results exchange. We are actually taking results from flow simulation to structural or FEA, and those can be things like around. Those can be only two things. One of pressures from which are liquids exerted on structure. So that is one thing. Second could be temperature. Now it not be temperatures, but what we are talking is about convection. Typically, when a liquid flows on a solid geometry, it will lead to heat dissipation from the solid to the liquid. And this phenomenon is obviously called as convection. This is defined by a set of values called as H, or coefficient of convection. So this can be understood and similar using the software. Around what I want to try, those can be exported from simulation to element analysis. So the only two applications I would say, the one that is shown on the image is more for the structure, where the fluid is flowing on the structure, you understand the pressures, etc. There you do the stress analysis on the component. These are 3 to 4 broader level application oriented capabilities of flow simulation. But a few more detailed things could be in terms of the kind of liquid or fluid that it can handle. So it could be a water which is not compressible. It could also be a liquid like fluid like gases which are compressible, which can be compressed and density can change over a period of time or as per the requirement. So those two different kind of both the liquids can be simulated. Second, Newtonian and non-Newtonian fluids. Typically, liquids like blood, honey, etc., do not behave as per Newtonian theory. They are a bit different. Obviously, when they are simulated in CFT, they act differently, and we need to tell to the software and handle them appropriately. So those are the those kind of liquids that the software can handle. Third could be laminar and turbulent. So typically a huge amount of examples will end up having turbulent flow. And of course, in many softwares, it is a very complex task. Set up a turbulent analysis, select appropriate model for setting turbulence. But in our software, we have a simple, straightforward. There are two different models, but one of them which is commonly used is K epsilon model, and that the software in itself gives the option by which we can say the flow can be either laminar or turbulent. So based on the situation, based on the requirement, the software will change the kind of flow it is going to happen, and it will handle it appropriately. And so there will be many different flows which are not constant over a period of time. So assuming the flow is happening now, in this case it is happening on a cylinder, the flow will not remain steady throughout. It will keep on oscillating, changes would go on happening. Means wherein the liquid is flowing on a particular object, and you see the green areas or the area after that, when the oscillations, and it happens forever. That can be simulated and understood using this capacity of flow simulation. So these are the different capabilities of flow simulation. Apart from that, as you know, we have two more modules. One of them is called as electronic cooling. This one is heating, ventilation, and air conditioning. Now, electronic cooling has one of the important capabilities which is called a Joule heating, where we can simulate the amount of heat created by a conductor when a current flows through it. So that can be simulated in flow simulation. It is an interesting thing which is required more for electronic equipment, and that can be done. From that, it has an extended database or a big database of electronic components typically used in electronic enclosure. So it could be anything like PCBs, fans, heat sinks, heat pipes, etc. So all those are available here with a ready-made database. Those can be directly used in the software. So this interesting fact, with this, it is not only the database, or it is not like a material property, but it is more than that. In sense, we are not actually modeling these components. So I am not modeling a PCB in its entire details. I am just having a solid component, and on I tell it is a PCB, Details of the PCB are given using the material properties. Right? Obviously, you can imagine we are actually saving a lot of time in geometric creation. Idealized representation will make it easier to understand, and we can set many scenarios easily. Obviously, calculations will be faster. So it is a idealized way of representing a certain electronic component using theory. That's all I can say about it. And few other things like PCBs, as I mentioned, can be simulated. It could also be heat pipes, heat sinks, etc. So those can be tested and simulated here. So this about, and finally HVAC, heating, ventilation, and air conditioning. Over here, it is more towards architectural details or towards designing of clean rooms, server rooms, etc. Wherein I want to that entire room is maintained at a certain temperature or at a certain velocity of air, etc. And typically, this is understood and discussed using parameters called predicted mean vote, percentage dissatisfied, operate temperature, etc. So this module has those capabilities to calculate these parameters. As well, it can, as we discussed in the previous thing, it needs an extended database to simulate all those things. So it has a big extended database of materials to which can do like again a huge database of fans, materials like wood, concrete added over here, and you can actually simulate them in more detail as previously. And finally, there is something called as tracer study. Frankly, it is a bit misunderstood concept and we do not use it effectively. Actually, this can help you understand the effect of, if I put it a different way, the effect of or a particular pollutant or gas would behave in a given domain. So if there is a closed domain and if there is a fire or some problem is getting created inside the room, we want to understand how fast this particular fire gets out of the room. So those kind of phenomenon can be understood and simulated using this particular tracer study option. And finally, radiation, another concept which we not talk and use much, but actually HVAC comes with this capability of advanced radiation, where we can simulate radiation, especially absorption of radiation in semi-transparent solids. So if there is a transparent solid and radiation is expected to pass through it, we can actually simulate and understand the details of how much temperature gets increased when radiation passes through it. Those details can be understood using HVAC. Yes, pretty much that's it. I'll give it a break for half a minute. 30 minutes. Any questions, guys? Please ask. Any questions of flow simulation? Okay, not, then I'll go back here. I close it. So I hope you have downloaded the new set related 2015 training manual files. Have it, please ensure you have this book, SolidWorks 2015. And as you don't know, if you could support training You see 20 related training files. Please download them. Uh, the finished version and the clean version are present in the same file set. I have them already downloaded here, and I opened a particular file from lesson 1. Okay, here it is. It's a collator. You can see here. It visualized in a better way if I can use a solid thing. That is not allowing me to do that properly. That's okay. This is the looks you can see here. It is a huge number of leads have been created. So take the unfinished or the version that can help me start from scratch, and later on I can get a clean version. This I open it. Okay, here. So this it is just or a casting of that particular collateral is shown here. There is part which is probably used for connecting further, so that is present here. These are two components which are present in this setup. So we are going to study let me open this. Those who don't know, and I would like to repeat it again so that we are aware of this fact. All these all these training manuals are in such a way that they have a case study based approach. So till they will have a case study, and we are going to try to solve that study. And it starts with an objective where we specify the steps or the learnings that one can expect from a particular lesson. So in example, you can see we'll be understanding model preparation required for flow simulation. If I quickly say something, it is more towards creation of those leads and creating a internal domain and understand how to create those leads. We can see the geometry for invalid contacts, which is very important. One of the common problems which you'll face when you are handling big models. Calculate internal volume, the amount of understand just a visualization or the absolute value of the volume that is present inside. Create a Solidus flow simulation project using the project wizard. Let's see wizard and do it. Apply flow boundary conditions. Going through the wizard, I'll try to discuss maximum options which are in the wizard. Apply conditions, goals, and of course run a solid and see the results. Okay, that's fine. So this is what I was trying to say. All training manuals of simulation have a case study based option approach, and in this case the case study has been described in this particular first of this text. So quickly go through this. We'll start. Prior to setting up our project, we will learn how to properly prepare our model. This similar thing. The problem description is given below. So enters at a certain speed, okay, and flows out through the 6 openings as seen in the figure. So inlet, we know velocity of the air, and outlet, we are going to find out at what velocity it exits at different outlets. Probably all these are at atmospheric pressure or even at a different pressure as per the specification of the case study. The one goal of intake manifold design is even addition of combustion mixture to the piston. This here optimum efficiency. We'll keep this in mind when analyzing our intake assembly, right? So if this is an intake manifold for an engine, each is giving fuel to different pistons. Obviously, all the pistons have to be working at the same efficiency, then it should be designed in such a way that the liquid or the amount of liquid that goes in at each one of them is same. That particular thing can be simulated and understood using flow simulation. So this is a case study which I was talking about. We need to understand this concept for each training example. Okay. Thereon, we prepare the model for the analysis. We'll get the lists. Let's see how do we do that. certain boundary condition declared, run the analysis. Okay. So who are not aware, from 2015 we have introduced this SolidWorks add-in button. So we need not go to the tools add-in option, but you actually have the option here itself where you decide which particular add-in to activate or disable. Simulation here. And in 2015 and may not be that much actionable is something like this. The formulation used to come in the top menus here, but now it has gone inside tools, flow simulation, and project wizard. Okay, it is a bit inside, a bit difficult, but that's the way it is. Of course, we do have this tool which can be used directly to create and analyze a flow simulation. This is what the you have the training manual as well as the examples with you, so you can do these things on your own. Okay, while I'm teaching, and of course, if you have questions, that would be great. As we discussed, we want to create lists here, right? So let's give this is the option which should. What happened to this? So yeah, the option is here. I just click it, create lists. Okay, it is telling us select planar faces at the opening. So things I just select those faces where I want to create. So see, apart from the central hole, there were two more which are present on the surface, and it has tried to create it over there as well, which is not required, but that's a work. If you don't want them, you can always delete it later. Here, so we observe closely. These are nothing but extrude features of SolidWorks CAD which have been created. If that surface, it will use it as the mid surface and extrude the body on both the sides based on its own judgment of the thickness of the geometry. However, if you want to change that value, you can go here and change it manually as well. So I just was checking the training manual if I missed out on anything. One other thing which I would like to highlight here is, yes, it is a bit painful to create these lists if there are too many holes. Okay, but in that you can also use something as shown on the screen here. It is a big place or a net which has been created. If you expect all these openings to be maintained at a certain constant pressure, then nothing wrong in using this kind of option. The option I showed you in the software, it will be useful only if we have different pressures at different outlets. Else you can create a lid, something as that shown on the screen now. You just create a solid geometry, close all the holes, and actually apply the pressure on this solid geometry. But obviously try to understand it will be pressure. It would not be a kind of absolute boundary condition. If it is a unit area or even velocity for that matter, it should be okay. After here we are assuming, or this will be useful only if the pressures are constant at all the outlets. In case you don't want these useless lists, we can actually get rid of them. Let me try to check if I can do that easily. One matter, even if you keep these lists, it is going to harm you in any way. But just in case you want to get, you can always do that. I am not going to waste time on that, but this can be done. Hmm? Let me check. There is some questions from David. Uh, could it for a non-prismatic opening? I don't understand what a non-prismatic opening. Prism opening in your case not. But what if it is filiated and forms a smooth curve opening? So rationale is very simple, as I told you. Uh, is nothing but the feature. Please try to understand. It is as simple as this. Nothing out of the way. Feature. Where did it go? Smart insert assembly feature. This is not okay. Here we see more of cuts actually, but at the part level, if I see the extrude cut feature, it is the same feature that we are seeing here. Let me try to show you that. So this particular feature, okay, is nothing but this feature. So just try to fit your thinking towards this feature, the view create. I select a plane, okay, I select a plane. Thereon I need to use the convert option to select the appropriate geometries. So probably I am required to set this particular thing, convert it, and then select feature, and then select extrude, and I'm going to select mid plane. That's it. So these six steps are reduced to use that ready-made option of create leads. Frankly, the new feature which was introduced around 4 to 5 versions back, so no, key style changes in lesson. Okay, so it was selected, and the limitations of what you see for the extrude feature would remain over here. If you're finding any other further complex geometries which you think a lead needs to be created, then obviously follow the strong CAD module, and they can always do it over there. Let me to Alex as a question. Is it lead creation tool only to work on planar openings? Yes, I say so, and I think that David is also asking about. But frankly saying that I have not experimented too much on circular openings. Yeah, I would put it in that way. Any other? While I'm with something. The most funniest way I can create. Okay, so I expect it to fail, but let me check what Flow says about it. The message is very clear. Planar faces space long to. So that limits everything. I think nothing to discuss on that. That should clarify it. Let me open that geometry again. Lesson 1 case study. Okay. No, gone. That's okay. Hopefully it should be fast. By the way, I'm not wrong, another software provides this kind of option. They talk more of meshing related creation of these things. And I remember when I used softwares like Fleet around 6 to 7 years back, they took almost an hour to create all these lists, etc., which is happening in a few minutes. So obviously it is a different thing or a special thing for us. It is possible only because flow simulation is integrated inside CAD module. Saying that, let me move back to the lesson. Any questions in the meanwhile? Now exploring the check geometry option. So we have created the list, okay, the multiple components, etc., which present here. You can tell the software we are expecting an internal flow analysis, and we can tell it to check how does it look. Okay, so you can see here once you do this. So one big fact, if it is internal flow analysis, before the load and boundary condition before is solid, please use this option. That is the only way you can understand if the geometry is ready for flow simulation. Okay, you can see we are saying is the geometry okay. Analysis internal is showing you the amount of fluid volume and the solid volume. Let me check. There is a question. To the opening geometry. It not be compulsorily a opening. Sorry, I did not understand this question. Sorry, it means does the lid a reference to the opening geometry? This question, Alex, can you please put it across once more in a different way? Okay, gets me written. Does the liquid? Okay, the lid change when the hole size is changed. I doubt so. It is not parametric, if I'm not wrong. I have not tested it, but I doubt if it is parametric. It appears as though it is a junk geometry that is created. It is not creating any reference to the geometry. It is just a junk geometry that is created. I think if it is parametric and it will change when the main geometry is changed. Okay. So let's see this fluid volume and solid volume. Okay, so this is what you see. Typically, if there is any hole inside this, now if a small experiment just to show you something, suppress, don't, okay, there is a hole here, and again I use this option internal flow analysis and say check. You can do volume is 0. And this happened because I had done a visible change in the geometry wherein I am creating a hole in the entire setup. So basically, this is an if this is a case wherein it is an internal flow analysis and it is not closed domain. Let me show you what happens if I use the external domain option. Let's see how it behaves. Acceptable for an external flow. Probably it knows the overall total domain that it needs to simulate, but it does give certain values for the amount of, or it is going to fluid and certain amount of solid. The exact volumes are shown over here. I'll close this and keep it internal. Okay, two options which I'll not show you now, but you can explore it later. One is create solid assembly. So you can actually create an assembly out of the things and create fluid body assembly. So this, compared to solid, the fluid body assembly is really interesting. This will, okay, first of all, let me, did I suppress or did I delete? Okay, I suppressed it. Let me suppress this. So this is me. Check geometry, create assembly. This will create a body out of the liquid that is present inside this domain. Okay. This now take other softwares, like again, if I take the example of Fluent or CFX, the rationale over there, the way it works is we invest a huge amount of time to create this this particular body, and thereon we just get rid of the solid geometry which you are seeing on the screen here and do analysis on that fluid body. Where software, we are not even worried of creating that geometry. The way logic in which it works here is very different and far more easier than what would have happened other way around. Oops, I can internal. That's dark fluid. So this is area which one needs to create inside other spheres, and thereon we start the analysis. Where it is seamless, and the way we did it is a very different okay. So it comes further in detail. But remember this checkbox. By the way, this as well as I'm sure if this lesson is going to cover it, but I suggest you can explore it later. There is also something called as open leak tracking. Okay, you can also explore this, wherein we can say the phase from which the liquid is expected to get in. Let me select. Try to select. Okay, while you also show you one more interesting option or a suggestion from my end for select surfaces, you can actually use planar surfaces to create cut through the domain. Okay. Not one. Let me try. Yeah, this looks better. Can I? Yeah, I can flip it. Can I take it inside? Yes, I can take it inside. Okay. Not too. It's okay. Let me show you the way I want to do it. Okay. So here we are selecting the starting phase. I select this phase here, and also tell the software on the uh, phase from which you expect it to go out. Okay, these two surfaces. Now we'll say mm, some section. So to show liquid, this no is happening. Liquid can come through. How it might go out of this system, something like that. It is giving a good idea of this. It is giving you the basis through which it might be going outside. But again, if there are any holes, it will actually not go all the way till here, but it will try to escape through those holes, and that will help you understand the location where those holes are present in the geometry. So very important. Again, one more important aspect of doing flow analysis, wherein getting or preparing the geometry for the analysis purpose. Okay. Any questions on geometry creation? Please be thought. And geometries are created as there are good knowledge base articles. In the present days, we may not face problems like this, which happen when we create. The past, the option of create was not present, wherein the list created manually, and user might end up creating such mistakes. But in that, please be aware, the best image is this one. These kind of contacts are not desirable in flow simulation. That is more of tangential contact or point contact. However, in that one part of flow simulation is you can actually have interference in the model. It's okay. Unlike simulation where it is not permitted, in flow simulation you can have interference in the geometry. It accepts it and proceeds. Rather, the way it works is it is going to yeah, here it is written. It is doing a Boolean operation of the entire assembly, and thereon it uses the assembly to detect the internal fluid or the external fluid, and the solution proceeds. Then it's okay to have if two faces or two objects interfering, but tangential contact is not permitted. or edge point to surface contact. So these things which I showed you a few seconds back, you can explore them, find connections. These initial tools that is they're handy for any analysis. You should be very comfortable with them. Now let's move on to the project wizard. Any questions as of now? Please ask. Oops, is both good and bad? No flow questions. Let me check the Q&A panel. Let me check this as well. Okay. Let me. The next triple or frequently used tool will be the wizard, which is present here. Okay. You can follow this wizard to do the analysis. So really, I give a name to it. I can tell which configuration that you want to use for this. Okay. Next important thing is the unit. Units, either it can be the default units or you can create your own unit system and select it. The way simulation permits, even here you can input in a different units and it can automatically convert it in the dialog box. So the dialog box is sensitive, so that is not a problem. But say that to have a consistent unit, and this one can help. Life will be easier if you have set the right unit for the more inputs for the output. It is easy to track, understand, and deliver the output. Here comes the more important, or here is what the important options start. First is what is called as an internal and an external flow analysis. I think now you are comfortable with it. Second, internal as well, there is some option as exclude cavities without flow condition. Most of you may not be aware of this, but if I try to show you with an example or an image, image, I just a domain. Okay, so probably the liquid is coming in from here. Okay, the liquid is coming in from here and it goes out from here. Okay, it is now whatever conditions, there could be one more object inside over here. Okay, there will be one more object inside over here. It is a, let me try to use my skills to show you object, and this object has a fluid inside it. Now this small object, a big object, a relevant object or irrelevant object, but it is there, and certain kind of liquid may be present inside that particular object. So when selecting this option, exclude cavities without flow condition, so this is a case wherein I am analyzing the flow only over here, and in understanding what happens inside or here. This is what this option is doing. I'm excluding. I'm not worried about the flow which is happening inside here. Will that mean the condition? and external. So even external, this comes into picture. It can also be a similar case, but it could be internal space. So two cases, both are actually. One is more of a cavity, other one is more of internal spaces which you think it's to exclude from the geometry. Broader level, visible important things need to be approached. Here in internal space, now for example, I'm analyzing a projector. I'm not worried what happens inside the projector or if it's CPU. I'm not worried what happens inside the CPU. I just want to simulate the fluid flow outside the space. That's it. So these two actions can be appropriately selected. Any other questions? Yeah, I my question. What the display in results in the cavity without flow? No results display. Yes, you're right. There would be any results displayed over there. It is like it would be treated as a solid geometry. It is a strong solid geometry. Any other? Look, around I also saw that comparatively lesson one is a bit longer, and I'm covering a few different topics, so it's fine. I would like to have a quick break of 5 to 10 minutes. So it is 10 a.m. in my laptop watch here. We'll start precisely at 10 a.m. again. Okay, we'll start at 10 a.m. Okay. A quick break. Uh, you to relax. Any questions as usual? The window is open. Please ask. Okay, it says that is the that I'm showing here available in Solidus website. No, it is not freely available. The one that I'm showing is here. It is for internal use only, so we cannot share it. But with the training manual, you will have access to an online version of the PDF. So there is a key which you can use online and you can see it, but unfortunately you cannot download it. Time wherein I said I can give the training manuals. So it was actually hard copy, not the soft copy. Soft copy we cannot give to anyone. It is more for internal purpose only. Okay. Oh, I opened too many files, I guess. Okay. Anyways, this is important for us. So, if you now we try to cover the maximum number of options in this wizard, but you should be left out because they will be specific to particular chapter. But I will ensure you understand the maximum number of options that are given here. The first something is heat conduction in solids. So all temperature comes into picture, and as well you want to simulate the heat happening inside the solid domain. They can actually use this particular option. Now, what is this option also, which is called as heat conduction in solids only. Now, interesting scenario. You can once I select it, many options went off. Dependent gravity, these things went off. So one thing is we are actually not simulating fluid domain here. It is only its domain. This, if a simple word, this is nothing but the thermal analysis that we might do in simulation professional. It is as simple as that. Okay. So this is about but the option is given here. You use it appropriately. On we have the radiation effects. We can select the by the not wrong. This option will be available only if you have HV module in software, and this is more towards this one, discrete ordinates. Okay, this is a different formation modeling. They have two different theories. One of them is transfer and ordinate. These two. Sorry. Be used, but the ordinates will be available only if you see. Okay. I'm not covering the theory at the moment, but if you are interested, you can always explore it in the online help. There we also can simulate the radiation effects. This is an interesting thing. But observe some more things here. If I select ordinates, you're getting a few more different options, especially absorption in solids and several characteristics. So these are a few more detailed things that you can give in the HT module. But the transfer model is simple as this: environment temperatures and discrete transfer. We can select solar radiation option and get all these different options like the details of how you want the setup to behave. In the sense, only we are specifying the location on the atmosphere or on the earth where this particular object is located, and database already has the details of the radiation that are present at that location, so that you can overrule our control is more towards the cloudiness, the angle, and a few small things, the day's time on which you want to simulate. So those things can be given in detail over here. But the value of the radiation, it can take it from its database. So let this next time dependent. So I told you uh, there can be flows wherein the flow will never become steady. It will continuously oscillate forever. So those kind of things can be simulated using the particular time dependent option. Okay. You can see here we are specifying the total analysis time and steps. So the time dependent analysis will be huge file sizes. Okay, the output time step can help you control the number of time steps that you want to save. So that one here, I select it, select it, and gravity. Next, gravity. Obviously have its effect, for I mentioned in simulation as well. Obviously any design analysis will gravity into picture. So can you select it? Number two, saying that you are saying that, remember, in both simulation the gravity effects will be visible only if the density changes. So typically if there is a liquid which is being heated and density changes, that is, it is a liquid, so the density is changing. So lighter part of the liquid can go up and heavier part can go down. So this phenomenon can be understood, visualized and simulated using the gravity option. So here you can see by the directions, etc. Then we have the rotation. So we discussed about the rotating regions. If you want to simulate those, then they can be played around over here. You can the default could global, wherein the entire domain is rotating and some parts inside it which are static. Few times or cases where it could be applicable, but otherwise it would be more of low that is sliding. Okay. Okay. Second one is the averaging. Okay. The averaging option was present in the past, and the sliding option has been added recently in the last version. Obviously, sliding can handle far more scenarios than the averaging option. In terms of not claiming anyone is more accurate, but what averaging can do, whatever cases averaging can handle, it can be equally accurate as does as sliding. Saying the sliding can handle a few more different cases than what averaging can handle. So for all examples you can use this sliding option, but obviously it is a bit slow. It will take more time to solve, and remember it is time dependent. So we are expecting changes to happen over a period of time, and those are understood and simulated. The process of simulating them in the software remains the same. When we do that particular chapter, we'll do it, but the process remains the same. Finally, reference axis. There are many different ways of explaining it, but basic thing could be with respect to a rotating region, could be the axis used as the axis of the impelling or rotating region. So those can we can also think in that direction. This example, so I don't want heat as well. It is just an internal flow analysis, and I exclude cavities even though they are not there. Next, okay. So first, global settings. That is more towards the fluid that is going to be simulated. It is as simple as you just open these boxes, go to appropriate fluid, either double click or press the add button. You can select it and remove it. Those things can be done. Into laminar and turbulent, as I told you, this software permitting this option, laminar and turbulent. Okay, so software can decide and take consideration at the appropriate levels. If not, if you are sure and if you want to enforce a certain kind of algorithm, you can actually select them, no issues. Next, another phenomenon, and of course to come, but to put it simply, you expect the pressures to be going very, very, very low, and it can lead to vacuum at those locations, and it can lead to a phenomenon called as cavitation, then just activate it. This will clear those complexities and solve the entire setup appropriately. Say it is not going to make you or help you visualize cavitation, but it is only imbibing those effects into the software. We need to understand cavitation only from the pressure distribution or variation. It's an option. If temperatures are involved, and these facts are also relevant, with more towards the wall conditions. Okay, so different things. It could be an adiabatic wall, that is no heat transfer happens. It could be heat flux, or any of these temperature options which are effective on the external walls of an internal flow analysis. Okay, those can be simulated. Roughness, if you are sure about the roughness, internal roughness of this entire entity, then those can be given. If that you want to or you want to transfer from some other flow simulation, those brought in or here. It could or that it is involved. It is nothing but the addition. Okay, there are different ways, but one of the common ways by which I explain this is we are in the software to start from an initial scenario. So when I start this analysis, software does not know from where to start, and it basically is starting from zero or ambient pressures and ambient temperature. However, if you have taken those initial conditions from some other project, or you are manually giving it to the software, honestly, you are helping the software to start with a more closer solution, and then it can further iterate to give you the final most accurate analysis result. Intensity and length. There is a one which says that what is the effect of roughness? So the results. What result is more significant with different roughness values? Obviously, roughness has its own effect on the flow of liquid. It can create, if you even imagine, when giving roughness, we expect the velocity to reduce at surfaces, and it can affect the entire domain. So see, if you know, that's why I said, if you know those values, then you can use it. So typically don't know those values. If value, you can try using it, and should reduce the overall velocity of the fluid. So these, as I told you, can be given to ensure a good starting point for the software. And finally, what remains is the mesh. Now, you know, this is interesting part over here is this is called as result resolution. Okay. I exactly forgot, but if I remember rightly, T5, that is 1, 2, 3, 4, 5. Software will try to improve the quality of the mesh. Okay, it is more towards the quality of the mesh. When we move from 5, 6, 7, 8, it is more towards the calculation controls as well. So it is not improving the mesh, but it will also give tighter controls on the mesh or the results, so that we can more accurate results. So that's the way it can be seen as a result resolution. But ultimately, mesh is also leading to good quality of results. So again, these things will be discussed in the next chapter, especially the meshing part of it. One is manual specification or the minimum gap size. So in my words, these are nothing but options which are going to help this software to create a good quality of mesh. So its own rationally to decide the element size, locations, etc. But overrule it and help the software by giving these values. So I'm saying the minimum gap. This is nothing but telling the smallest area or the cross section through which the fluid is expected to flow. Other round, we also have this option of manual thickness, wall thickness. This is more towards the minimum thickness in this entire geometry, which needs to be captured, and the fluid should not affect it. Even that can be given out over here. Okay, so those two parameters are present. And this is an interesting thing, something called as optimized thin wall resolution. Now, typically, if a geometry has small walls, okay, you can keep this active. The the interesting part over here is, even is not created appropriately, or it is not showing that it has captured the thin wall, but the software will ensure that those are captured properly using particular option, so, algorithm rather. So if you want to do that, just keep it active. How you are giving manual mesh, if you are controlling the mesh on your own, this has no significance, do not use it. Narrow channel refinement. The second one is this one. This different in the sense, previous one, as we were discussing, it was more towards the thickness of the geometries. This is more towards the amount of, or this area of the liquid through which it is flowing. Okay, so we're going to those refine on those aspects and things. I think that's it. So yeah, small wizard, it can be finished in a few seconds, but I took almost half an hour to explain it, and I believe that is that explained in detail most of the capabilities, or the things that will bring in due course of chapters. So we are taking a lot of time in this first chapter. We have understood many more things even for other chapters, and that will help me go a bit faster in the remaining lessons. Okay. Okay. So here is the setup. It's already. There are different ways of applying boundary conditions. As I told you, one of the simpler ways could be make it transparent, or you can cut section that will help you select the internal faces. Those options can be used. Let me check the training manual if I missed out on any important thing. It should be okay. Yeah, we are moving into insert boundary condition. Guys, that's fine. Let me check. Sorry. The radiation intensity, where you can specify, would be able to specify the convection coefficients to be applied in this. This can be done. The only difference is, let me quick show you of this thing. So totally, the options which are present in the software are driven from here. So not activated it, they grayed out. For example, I cancel this. Let me with this one. If I go to flow simulation, okay, you can see there are many different things like the electric. If you have the electronic cooling system, then these options will get activated. You can see radiation related options are over here: radiation source, radiative surface, and convection. Where did it go? Convection is also available. That's it. But if I do a simple thing, go in settings, activate that, or when thermal effects are activated, we need to give a material to the solid. Okay. Yes. I do that. Now if I go to flow simulation, you should be able to see those options. Oops, these two ones are more towards mm, yeah, HT model, I think. But why activated? What did I miss out again? Is something more than I need to do. Oh, I thought I activated it. Sorry. Insert. Yeah. Now you. So these are two things, David, which should help you. Second is surface sources. Let me see if it is permitting convection here. Heat generation, surface generation. Not these two. Where apply convection? I forgot. You can apply actually, but those boundary conditions. Is it giving us transfer conditions? No. Boundary conditions. Openings. No. No. Real like this. So David, the convection can be applied using this option, the wall condition, and you can select maybe outer wall, and you can give heat transfer coefficients directly. You can surface. So the options are somewhere over there. This is not related to this chapter, but there was a question which I thought I should clear. Let's go back. Yeah. So in case we are just applying a certain amount of fluid flow rate, that's the switch which I use personally, and I just click on the extra thing and just say select other. Typically it will jump onto the internal surface of the lid and we can select that surface. Okay. Okay, this was under wrong thing. Select other and select the internal phase. So yeah, there are different options which will come into picture. I'll quickly scroll through them. One of them is this one, wherein we are selecting the appropriate surfaces, selecting the coordinate systems. If at all you want to play with the references, directions, etc. So we do that. These will be typically most of the boundary conditions that we are using in flow are vector quantities, especially velocity, etc. So you might want to ensure the axes are correct. Then we can specify either mass rate, volume flow, velocity, mass flow, volume flow, or it is specifically saying whether it is an inlet or an outlet. So you can set appropriately, but the only big difference is in one way or the other, it is specifying as if it is a negative or a positive. That is, if mass flow is coming inside the domain, it will be positive. On the surface, if I use the same inlet boundary condition and give a negative mass rate, that means that it is going out of the system. It is simple as that. The options of how it is coming. So it could either normal to the face because it's fluid, so it is not as simple as a structural analysis, and it could also be swirling flow. That is, it is swirling inside. It is creating a swirl and coming inside. Okay, it could be also that way. And if it is a swirl, we expect it to happen, then we need to specify other parameters like angular velocity, and uniform, whether the profile is to be something like this, which is typically for most of the flow conditions. It could also be a vector quantity, that is, it is not coming absolutely as per these two details, but it is of a vector and you want to simulate it appropriately. So those can be one. Okay. Second thing, if I remember, how much was it? 0.05 meter cube per second, right? Oh, let me. I did not take the unit, but does not matter. Per second, check if it takes. No, it cannot. Okay. Next unit. What am I taking? Sorry. It got stuck. Okay. Let me select this and then one flow rate, meter cube second. Fine. Okay. This looks okay. So move ahead with the other parameters. Okay. As I told you, this can be uniform or can specify a full developed flow. Those who don't know, typically say if this is the inlet, this is inlet, the T profile at the inlet will be something like this. Sorry, it should be exactly the same, something like this. Okay, it will not be straight. It will be straight. It will be less at the surface and more in the center, and obviously surface roughness is creating this effect. So we select fully developed, we are saying the velocity profile like this. It will assume the velocity to be uniform or straight at the inlet, and solve it is going to create that kind of profile. So appropriately, you all have these function options here by which can give a form as well, and the result as per this formula or value dependent, but is then we can select time dependent variations as well. Thermodynamic parameters, if it is in inlet is coming at a certain temperature, that can be driven. Turbulence parameters, you can see, as I told you, we have two different turbulence models, or the way we can define it. One is called turbulence intensity and length, and second one is K epsilon. Both are very, very involved topics. Knowing these values is almost impossible or difficult at our levels to find out. But it is okay to leave them at the default value. Okay, we can leave them at the default conditions and let the software the rest of it. Typically, for most of the scenarios or in the works of the developers, almost 80% of the turbulence applications or where turbulence is expected, those can be handled using the KSLN model. So for all practical purposes, it's safe to use this particular model. If saying turbulence intensity and length is also equally good, and if there are certain scenarios where you want to play around with different models, check, or this model is going to give a more better results, then feel free to use it. Fine. Boundary layers can be laminar or turbulent. Now, again, interesting topic. Boundary. What is boundary layer? Let me again try to. Is this no? Let me do this. How can I view this option? Let me take a view using X. Yeah. Let's my pen again. Okay. So I think this is A, and the flow is happening here. Okay. This solid entity of on which it's happening. So typically, the variation of velocity happens at a certain thickness. Okay, certain thickness from the solid entity, and this layer is as boundary layer. Okay, this is called as boundary layer. I have to write. Okay. Now, where this behavior is something like this, that is uniform, varying separately, thicknesses are changing, or it is a bit different and it can blend, so that you can enforce and tell the software over here. You decide and tell it. Okay. And finally, create associated goals. So typically, if I am applying, discuss a bit more on goals, by the way. But in the while, when I'm selecting this option, I'm just saying that any particular boundary condition is well converged. So it is not that it is not going to converge. Okay? Selecting it would that we are telling the software, yes, this is important for me. Ensure it gets converged appropriately. This I will just scroll the training manual. Okay, one, I think I missed out a few more things here. Most important was this one, which was flow openings. So we have mass, okay, and velocity. These were there. So mass, volume, and velocity. Second one could be pressure. In terms of pressure, we have environmental pressure. I think other options remain the same. Yes. We have pressure, static pressure, and total pressure. So the ways of thinking, but one basic fact, or they want to, where I can suggest is environmental pressure can be seen as an initial condition, and software has the flexibility to come up with a final pressure at that wall. Second, we also have static pressures and total pressures. You can see here. These two I will discuss a little bit more, but put simply, total pressure is the summation of dynamic pressure as well with the static pressure, and static pressure are more the way in which they are measured practically, depends the values that you have. But most of the times we end up using static pressures which are known dynamically. There is a lot of text on this topic in the training manual. I'll try to open that and explain it in more detail. And walls, we already saw this. First of all, real walls are also useful in conditions wherein you have created that rotating region and you want to enforce or tell the software that this particular wall is not moving. Okay, we'll see more detail when that chapter comes. Something called as an ideal wall, which is nothing at that wall. Walls, as I told you, those which are exposed to the atmosphere, but we are not simulating them in the software. We just tell boundary conditions as those exposed walls. So those are these ones. Wall and real wall. Now coming to real wall, here we have different options. We are specifying internally. One is the temperature, second is the heat transfer coefficient values, and any roughness that we want to give, and finally motion. This thing now, seeing this option, it might appear that we are simulating moving wall condition. That is, the wall is actually moving, but the fact it's just setting the effect of that motion. So, I mean, there is a wall, it is expected to move with this velocity. More time it will be parallel. It is not penetrating inside the fluid, but it is going parallel to the fluid. We are just simulating that effect. That is, the velocities created by that wall are imbibed and simulated inside the software. Okay, what is happening here? And yes, it can be linear as well as it can be rotational. These can be simulated. Yes, what the options which are present in boundary conditions. Directions on this topic. Please give questions on content that we have covered as of now. Okay, then we can change the value of environmental pressure. Is it the same with static pressure? As I told you, environmental pressure is more of an initial condition. Okay, we are starting point for the fluid flow. Here values that you are changing, they are just telling it to be the initial condition. Whereas static pressure, the way we use it in the software, is nothing but an enforcement. That is, we are telling, irrespective of any other changes, the pressure at the surface remains what giving to the software. That's it. So that works, Simon. Any other? Okay. Because these boundary conditions, I don't have the patience to use them appropriately or correctly over here. So I will jump onto this study. So in this case, what we are giving is a flow rate is given at a certain surface. Okay. we are 0.05 meter cube per second, and no other changes are being done. Okay, just let volume flow rate is given, and all other outlets, okay, we are giving a static pressure condition. That's almost similar to environmental pressure value. So we expect the outlets to be maintained at that pressure always. They have the goals. One is the volume flow rate at the inlet. So now there are different ways of discussing goals, but two important things which I can orally put across is this thing. Now, irrespective of the goals that we specify, software will try to converge on most of the global parameters. Okay. Number two, the goals are more relevant for you to control the way the solution is going. I want to ensure a certain output. That is, in this case, I want to check the velocities, volume flow rate at each of the outlets. I want to ensure they match and they are consistent. So if that case, then I can create a goal so that throughout the solution I can monitor how it is going. If the results are out, we can actually go to that particular goal or value. So it can be either seen as a goal or it can also be seen as a sensor which is present in simulation. But a sensor which is only monitoring, they also enforcing certain things in the software to ensure that we other way around, we are telling what is the most important topic for you to be converged or got. So the way you can think of goals, there are more detailed definition, but at a broader level, this is what I would like to say. Volume rate, yeah. So where was I? Yeah. So the inlet, we are monitoring the surface volume, and same for the outlets. We are controlling, giving a goal to monitor and converge on the volume flow rate. Okay. Fine. There are certain things called as equation goals as well. You will get this particular front end. You can actually directly create an equation here and visualize, or sorry, not visualize, but actually find out values. In this case, you can see here there is an expression which adding the volume flow rate at all the 4 outlets. Okay. Now, example, if here I get rid of this just to show you how it works. So I directly select this thing, class, select this, class, I can go. Obviously, as you can understand, oops, I did a mistake. The inlet volume flow rate is going up, the sum will be same, right? And I did a mistake. So this will be equal to inlet volume flow rate. Okay. So then and that means are already there. Not that. Okay. Let it. This is it. This is the overall setup that can be created. It's an interesting thing. Unlike many softwares, and especially if you're comparing with simulation, this FowSimulation allows you to monitor the results even when they are solved. This is an interesting fact which can help you because unlike simulation where we trigger a solution, we have some solution irrespective of testing. But here FowSimulation, we're talking more about something called as convergence. So not be the final solution, it is in the process and we are actually just see how it goes in the process. So we have this option at the top here, insert a preview. While the solution is actually going or happening, we can actually visualize the result. Yeah, this should be okay. So one could be, I'm just visualizing it and try to have other things like a vector plot, the way the fluid is flowing. I can decide which result I want to see. Letter velocity apply. Yeah, here it is. All these things can be visualized while the solution is going. You can see how these goals are going on. So the values over here. So obviously you can imagine the sum of those 5 goals is negative and inlet is positive. So these two should obviously match for a good convergence. Okay. What is my goal stable is fine. You can pause the solution anytime you think this is good enough. You can always stop it. No need to wait till the software stops it. Software stops based on the concept of all these goals, based on calculation control options that we are given. We'll show you where those options are. And so typically flow solutions will be huge, running for hours or days together. So this window can keep you a good feel of what is happening in the background. Okay. Before I proceed to the results, I'll see there is some questions here. Questions are if we can change. Okay, I took this question. If goals are not set, what results will be used to convert? So this is what I was trying to highlight. If two of the goals being set, all parameters, that is velocity, density, and temperature, if at all they are there, at the global level, software will ensure that they are converged. So you can try any iteration, you can delete goals, and can expect similar values even without giving a goal. It does not matter. Okay. However, if you want far more accuracy, you want to have more controls, as what I told you here, you can actually use this goal. So and I think we have this table here. Okay, by the way, remember this thing, calculation control options gives a bit more detailed front end over here. Okay, okay, solving. I just have to check if I can show you that. But in that, once the auto convergence, even though you have created the goal, but ultimately software is converging in its own way. Okay, in its own way. However, this can be changed to manual, and you can actually give the value to the level to which it needs to be converged. Okay, even that can be done here using this. Second, to stop the solution, as I told you, this is a convergence, not a final solution. So here there is like criteria to stop the solution. It could be number of iterations, it could be goals or anything. So one could be criteria. If one goal is satisfied, this is funny and this is a fact. By default, the software is selecting this option. Better select all. I actually end up doing that to ensure I have created are converged. I keep running the solver window. If I'm satisfied, I can stop it anytime. Does not matter. But software struggles to meet all the goals. Okay, this is important. So typically in flow simulations, remember the final results may not be final. See, convergence plot is very, very important. Let's cancel it. Okay, what is the second? I think I answered one of the questions. Can we set the convergence tolerance? Yes, we can set. So this is the place where you are setting the convergence tolerance. These ones. Obviously, are driven from the goal. And you are nothing setting the convergence tolerance. Guys, goal important topic. Ensure you have understood it well. I missed out on showing you this. Let me run. Okay, right. But yeah, aware this window has a few more different options. Okay, if it is there, you can only solve it. If this is done to a certain extent, you're not happy, you actually add a few more goals and continue the calculation. Remember, this is an interesting topic which you can do. You not start from the starting. Like if a crash or something, take previous results are there. Okay, in terms of processors, you can see it can be, if it is on the same present machine, you can select the number of processors that you want to be used. I'm showing only 8 processors. I thought my machine is 16 processors. Let me check. CPU, number of processors. Got 100. Memory, Ethernet, Wi-Fi, app history, users, details, service. Okay, forget. I'll not get into it now. But here you can put some Wi-Fi on my machine. Okay. What it is, you can also have an option by which you can solve the computer solution on another machine. Okay, you can give the name of the computer here, you can add it, comes down here, you can say okay, and the solution we triggered on one more another machine. uh, the process or the cups or the steps that need to be followed to do that can be found online or in the domain. I'm not covering it in this training manual, but if any, please ask. I can help you out later. Saying that, remember, or rethink on this, but whatever I remember, the thing always happens on the local machine, or solving happens on the remote machines. That is what it is at the moment. Hmm? And finally, results for load results at the end of the solution, batch results. Yeah, if you want, you can actually trigger batch options from here as well. Okay, so I told you the run dialog box is a bit more capable and having more options than for right click run. Any questions, please ask. It is string manual, then I'm looking at page number 35 now. So we are almost at the end of chapter 1 and 1. Okay, the distributed solving to multiple computers. No, at the moment, no. It will be only one computer. So if the guy has one strong computer where to trigger from his present computer, he can always do that. A few companies are offering distributed computing, but comes at a cost. It is not for free. Okay. Now, the cost is actually 4-5 times of the cost of the software. So it is, if for example, these are not absolute values. If FowSimulation is costing me $5,000, I understand rightly, they are offering distributed computing to as high as $20,000. The rationale is very simple. You have a lot of time, and typically people do not buy this outrightly. They buy it only, they have the solution, so they buy it for a few months or days, they do it, and then they use the license. Of course, there are companies who buy them outrightly as well, but that is. Let's move on to solution. So typically, if it is the present configuration and if you activated it, this will get loaded. You can always click from file. Remember, the file which needs to be loaded is 1.fld. Okay, this particular file, and when you click that file, it is giving you details of that particular has been saved. Okay, and typically, if I remember rightly, yeah, this is one of the initial iterations. FLD CPT is not used. Okay, cancel. Okay, then on, I can create something now. And again, unlike simulation, we never see the results on the entire geometry here. In the sense, we actually it results internal to the domain than what we do in simulation, where we typically see the results only on the surface or the external part. So we are actually penetrating inside and seeing. So what of interest to me, let me get rid of this computational domain. Okay. So to me, I want to see at a particular cross section. Can view so that I can see it. Yeah, it's not good. That's okay. I can actually see the results. Now, right click, cut plot, insert. I think this should be easy. You can do it. I'll go through these different options, but at the moment I'll cover these things. Plot it. The or the result thing is active here. You decide which result you want to see. You can set them and plot it. Temperature does not make sense here. I set and plot it. Okay. Second, also add more parameters. So if you want more results, you can actually click add parameter, add them from here. If the quantity which is available over there, you can actually get it from here. Okay. Second, remember, you can reset the values. By default, in all result plot, it is going to show the global value. How you want it for the local plot, then you can actually click this. There are two buttons over here. Reset global minimum. Okay, global minimum, or set to plot minimum. So that is, in this plot, show me minimum value. In show me the maximum value. Remember, or unfortunately, by default, I would have liked it to be plot specific, but there are reasons for that wherein they kept it global and continues in that way. So remember to do that. Sometimes the interpretation may go wrong if you are not aware of it. Car is quite sensitive. It has many options. You can see the number of colors that you see here. Okay, too much actually. I should not. Okay, yeah, 1, 3, 4, 5, 6, 7, 8. Okay, it should be fine. Okay, what can be manipulated here? I can can be moved. The contour can be moved. Okay. When I do these things, velocity, same thing. Outrange is okay. Color palette. Oh, this is fine. Okay. The options which I would like to discuss here is this one. When you go to a definition, the cut plane options are there. You can decide the location. It can be simple contour plot as shown here. You can isoline plot as well. You can plot it appropriately and see it. Let me refresh. So you can be in the form of isolines and a vector plot as well. Okay, with the colors. There is a different button called as detailed preview. So when that, without using the window, it will update the front end. Okay, we do that. Okay, here is it is. You can see the way the fluid is flowing. The new options which was added in the last version is this one. Oh, for given list. Okay, my graphics card is not ported. It's interesting. The I'm using is a comparatively new laptop. So I think I need to check on if I need to update my graphics card driver. So I get that message, but in the meanwhile it is doing something. But I'm afraid that because it is interacting with the incorrect graphics card, it might lead to a crash. Let's see what happens. So streams is an interesting option which came up in the last version. It can actually help you visualize the results in more detail. The most interesting part of this is when you zoom in and zoom out, the streamlines get updated. So the visualization is nice irrespective of your the zoom levels. So the interesting part over here. And finally, meshing. Function you can actually visualize the mesh, only the mesh without the result. So these also be cases wherein I'm not seeing the results, only seeing the mesh. Okay, that can happen, and this option helps you do that. The software is getting into a mess with the streamline option and interacting with the CAD card. Let it go on. In the meanwhile, I think we almost covered 2 hours. The last hour is there. For covering lesson 2 as well before we leave for today. Let's see how it goes. But in the meanwhile, I think for a break, let's take a 10-minute break. It is 11:02 now. Let's get back at 11:10. Let me time here. Let me give my laptop to recover from this crash. If at all it is a crash, let it is doing. Thank you. Let's take a 10 minutes break. We'll meet again at 11:10. Thank you. Okay. So to restart the software because of the client related problem. That's okay. So when I told you we see the results, you cut plots, even surface plots, etc. So unlike simulation, it is not a straightforward result. We need to decide what we want, where we want, and see them in far more detail. Second, remember the global plots are not at the local level, but they are actually at the global region. So we can appropriately and plot it. Okay. In the final trajectory, I believe okay. Mesh plot. Okay, let me show you the mesh also. And you may be also interested in seeing the mesh in 3D. You can see it. So there are options to show the fluid cells. You can also see if you want the solid cells. Let me check if dynamically update it so that you can see it. Apply. Let me call it. So this, if it is complete cells, it is something like this. You can see they are actually brick elements. So that is the why. That is one of the reasons the meshing is comparatively faster here. Saying that also not covering the entire region, but there is something called as partial cells, which will help you get. Let me check if it here they are all. So this will ensure it is covering the entire geometry, and it does not mean if it is overlapping a solid and a liquid, it is not covering. But the partial cells have the capability wherein certain part of those elements can behave as a liquid, certain part can behave as a solid. That helps in ensuring. But these are a few options which can to visualize those in the 3D. Frankly, does not make much sense because it is difficult to understand what's happening around, but the option is present. Huh? More of these 2D plots with mesh can actually show you those details. If I yeah, transparent. This is far more relevant and can give you a good idea on how the mesh is created. A plot or a cut plot with mesh only can show you far more details, or more, or the results that can come from this one are more interpretable than the other one. And I think I saw some question coming in. Difference between results of surface parameter and surface goals. What is results of surface parameters and surface goal? It is absolutely same, no difference. Surface goal is, as I told you, it will be goal will be used for convergence. It will ensure that convergence is happening. Whereas if at all, as I told you, you are not created any goals, then use this thing. That is volume parameters, surface parameters, and point parameters to see results at a certain point or etc. So other forgot on creating a certain goal, then you can use this to like this to try to just hear what I'm saying is correct. So if I say volume flow rate internal surface, you can see the value. It is 0.05. Okay, 0.5. This is the volume flow rate which you will see in the goal. Edit definition. I'm selecting inlet volume flow rate. Sure. 0.05. So it is absolutely the same. So helps easier, makes it easier for me to explain. So you have surface parameters similar to goals, volume parameters, and point parameters. If at all create and visualize it, except you can see the results in the form of goals. Graphs. Okay. So any particular thing you want to see graphs, variation, or a bit of length. And again, frankly, not much use because unless you want them specifically, these may not make much sense. But those are available, you can always see it. So now it across X, which is 0 throughout. These options are present. You can explore it more from. Yeah, of course, you can create a sketch and then try to do that sketch or something like that. Yeah, this is a. Yeah, discuss goal not saw a report, no big deal, and created animations are interesting, we'll see later. One thing is these two things. Okay, flow trajectory. Typically, I have the option here to select a surface, the location from which I want to calculate the flow trajectory. That is, it is going to show you the flow is happening in the form of I would arrows or lines with arrows. Like surface, what am I doing? Let me review and try to do it. Or I'll a cut section or else. I think this it is the internal surface. Oh, no. No, by option to select such a surface, you can select the boundary condition. Okay, select the boundary condition. Okay, you can directly right click, insert. Automatic surface will get selected. In case not aware of this option. So some lines with arrows, you can select which you want. So it is not only the lines but arrows as well. But bands or the spheres are also nice. They are as if small things moving around in the body. So let's see. Any concept you want to give for corporate region? Showing the time. This is time, by the way, for which the flow is happening either to and fro, one way, two way, all those things can be selected and ways. Did I lines with arrows? It looks like only lines. Let me recheck it. The arrows are very small. Anyway, in the animation as well, they should tell you. A good idea. I think one thing which I missed out here was that one. Let me yeah. Always remember to reset to the local thing and then only see result. Okay, what it is. I think the particle study we have a separate lesson on it, so I'll keep it for that. But these are the different results that one can see, and that's what it is all about. So, got a few minutes. I'll just scroll through the training manual to check if anything else that I have missed out. I need to show you. I think you can explore it. The option is here. You can add which particular plot you want. I would not like to cover too much on this. I believe it is self-explanatory. Other way around, it is a bit involved, but you can play with this option to realize and decide what you want to do. Since it is not too much domain oriented, more of an option and the process. You can just explore. The page number 38 explains you how to do it. Surface plots we discussed. Probe, should I show it or shouldn't I show it? No big deal. Decide this. Let me do this. This contour. By the way, as well, you can explore it later. Just the way it is. Visualize the absolute values at a certain location using the probe. You can play. direction, it is a straight. If velocity, then we may be able to see direction. Let me check. So other way around, you will see certain parameters which are more in the form of this way, wherein on that particular area, it show you minimum value, maximum value, the average value. Okay, minimum, maximum. Unfortunately, here it is all the same, but it can be this way. And there is also something called as bulk average. Now, this is a interesting quantity which is most of the times it is, but it is considering the location and the distance from the averaged point, and then it is more an equation. The line help gives an way it is calculated. So it is considering the distance as well as the location to give you an average of the entire thing. So it is not a simple average of addition of all and dividing it by the number of points, but it is more to that. Some quantities you will find these things being done, that is bulk average is available, but certain quantities it is not. So that is one thing. Guys, give a thought in terms of results. If you have any questions, please ask. Okay, I got the question on bulk average. What is the okay. Bulk. The best way to explain bulk average is, where did it go? Let me check. Not this. This. No. I think I'll go to online and help. This is the best to do. Help section, help topic. Search. Let me send directly. No. Prefer this. This. If then explain, then this is what it is. So average is as simple as this. The function. This one. And you can see it is doing a few more things wherein it is considering the as well. Okay. Now, the question of where to use bulk and where to use average. For purposes, obviously, bulk I suggest. Okay, almost both are average, no doubt on that. Okay, so they are not giving us any absolute sense at that location. There could be some cases. These are application oriented. The user needs to decide what you want, how he wants to see the results. Average may not be is a simple value, as you saw. As I'm saying, it is taking the average of those locations and dividing by total number of cells, etc. So that's the way it is. It is simple average. Whereas average may be more representative, actually in cases where density variations are happening and the relevance of the values location is far more important. So frankly, I don't have a one-line answer for this, but first of all, what it is, I think these two equations tell exactly what it is about. And I would say it is more application oriented. Okay, in this case, I'm happy with average. In this case, I want to do more accurate. I expect funny things to happen. I'm going for bulk average. But basically saying that typically one might also plot a surface plot at that location and see the maximum values and minimum values as well. So this is how the user wants to see it. If it is a comparison with practical testing, then sometimes bulk average makes more sense. It could be, if at all we don't know the location where the testing is done, then the average can be taken. But saying that again, I repeat, I don't have a one line answer for this question, but the help gives you the equation that is used. And results, you'll find many different options. Please feel free to explore them. One of the save image. So there are options by which you can save images from the event into a bar here. Okay. The obviously is level. I can it runs. Hopefully mine is registered and it will open. Register is going to be done. All other options like videos, summary is going to give you the details. By the way, if at all you have all the analysis and you want to share some details with others, your summary is useful. That will give a quick overview of your entire model setup, rather the setup. What else? Load, probe, display, delete, plot manager, max table, compare. Okay, compare them later. Hopefully, okay. You explore these options. That should be okay. You should be comfortable. Yes, pretty much that's it. So guys, we're almost, or we are done with lesson 1. So seen the capabilities of flow simulation at a broader level. Questions, please ask. If not, I'm moving into the next chapter, which is on meshing. And let's break. Please ask. Okay. What is the bulk error? When you get the point results, is the result referred to the node of the cell, just like in FEA? You can think in that direction. But remember, FEA is using finite element method, and CFD is using finite volume method. Typically in CFD, the calculations will happen at the center of the cell, whereas in FEA, if you remember rightly, it is not just nodes, but it is actually calculations are happening at the Gaussian points, and nodes are nothing but the averaged values. So you might want to compare those results with elemental results of FEA and not nodal results. It's fine in terms of understanding that the probe is giving the results at the nodes. It is actually mapping to those nodes and giving those results. Please, for another half hour, will be the meshing part of it. I did stuff sitting alone somewhere else and listening to a involved topic like flow simulation. It's tough for me to talk sitting alone in this room here. No one in front of me. I'm just saying this morning time speaking, but it's fun. Section is these questions, so please use it. Don't worry how difficult or easy that question is. It is us to learn. So it will snap to the appropriate location and give the values for us. It may not be at the exact location where I'm probing it. Let me check. Let me zoom in. Let me show you the mesh also. Edit definition. The mesh as well. And this is where it is. And so it will be showing at multiple locations, but I think side or here. This big contour plot, it does have values all across the thickness. So it's showing a color plot, and it does have those values. So yeah, I would put it in a different way. Unlike um, here it is snapping to that location. We actually having the values, and it is comfortable showing those values inside as well. So Alex, I think I would put it in a different way. It can show the results anywhere inside. So let me go somewhere else and probe it. Yeah, let me get in here. But in flow simulation, we may not be worried about this level of accuracy. It is to expect, but yeah, software is permitting to give you those things. Yeah, different, and it is calculating them. Fine. In one line, it is not snapping, but it is giving the values at that location because it has counterplot and it has the values for the locations inside it as well. Wow, nice. Not only giving the probe, but if you observe the labels that are coming here, they are getting arranged well. So they are not overlapping or doing any funny things. They are really arranging themselves well in a particular order. Good to developer. Yeah. Any other things, guys? Okay, let me get into this example. Now I discussed many things. Okay, first of the wizard. Okay, the wizard that we were seeing is actually can also access. Now if there is a already created study, always go to general settings, and I can access the same settings as those that were given in the wizard. Okay, only they have separated the mesh part of it. That's it. All other things, analysis type, fluids used, all can be accessed and manipulated after the wizard has been used as well. Okay, number two, let me go to something called as initial mesh. So these were the few the options which came in over here. Okay, instead of spoiling this, I think I'll need to play with a few different things. Okay, let me open the clean model. It will allow me to do many things than the default study assembly. So then now we are discussing the meshing part of it. So any questions on meshing, please start asking. It is. Now it is the same thing, but you have kept the project to be clean. Okay, fine. Flow simulation, wizard, next, any liquid, I think, but you are all experts in this topic. So okay, here it comes, the meshing. So as I told you, let's do the default thing first. That's result resolution of the default. Accept it. Let me solve it. But as I told you, we do have an option to only edit the mesh. We need not be worried about solving. Okay, run. Whatever. No things which I don't want to do. It will take a lot to do all that stuff. Okay, yes. It wants. You can see the meshing is actually considering the loads and boundary conditions as well. It is not a dumb mesh. It is more intelligent. Not only geometry, but it is considering the details of um, bottle. Okay, fast. Let me get into general settings, internal. Okay, I do not want the complicated stuff. Yes, it has done it. Okay, I do this thing first. Okay, I back to low. I don't want any settings. Any settings. Let me do this. Let me try to solve it now with the could be. I don't spoil this because I want to give you all the options without me spend much time on creating those options. So let me go here. Let me create a clone of that. More clone of that. So those who don't know, there is an option to clone your project. Okay. This setup is ready for you. So I go original which I keep. This I use it for testing. This one so I okay. Let me test it one. Okay. Here I will change the initial mesh. I take the automatic setting. I take the 3 units. Here it is. Hopefully this will mesh with the setting and telling us how it would mesh if the setting was global default. Okay. It's preparing the model, meshing and returning. This is a case where I have used a wizard. I use the default initial mesh setting of 3 and meshing it. Okay. Use that. Let's have a look on how the mesh looks. While meshing, I would like to highlight. So one, you saw the default initial mesh, that particular bar which is present, which can be used. On you have the some options in terms of doing the thickness, that is the gap, minimum wall thickness gap, and liquid gap. So this is the second control that we have. Third control would be more towards absolute. Given a particular cross section or a plane, I can specify how many elements I want across the thickness, how many so mesh. Okay, I can stop talking. I can see the mesh. Let me show you the mesh. Here it is. So no. So interesting part you can see, even though I have used initial mesh, you saw I did not do anything else. I just used this one. Initial 3, optics involve resolution, and then it knows where are the boundary conditions. Okay, even with this minimal intelligence, it to create a appropriate mesh for it. It is not worried, like we may not be worried too much about what to do. And more, like let me try to do this again. Which I would like to highlight more based on my own experience. This option is present in the software. You can use it. I have the more intricate option of what we'll discuss now. Saying that, my own personal experience, the initial mesh option itself is far strong. I've got many intricate model where people have played with the different options. They have manipulated the things. They have come back to me. I just go use the default initial mesh and I get equal accurate results or better results. So the point which I want to highlight, the default initial mesh algorithm is far more stronger and can handle complex scenarios than what we think it can. It is more intelligent than we doing the mesh manually. Okay, so remember, coming back to my point on the different kind of meshes that can be done, controls that we have. Apart from the initial mesh, apart from with the thickness of fluid or the geometry solid, other options of giving number of elements across a certain plane. That's what has been done in this example. We also have an option to give local mesh controls. In the sense, I can create a local dump geometry which can be disabled. However, that geometry can be used to define the number of or quality of mesh inside that geometry. So that can happen. So that are the only 3 to 4 options that are present in the software, and for all practical purposes, the initial mesh option is far stronger. And the next best that I can suggest is use the geometry option. That is, you select a certain area and tell the software to mesh for that. Okay, let's see how it looks now. Okay. Just has created a different mesh and in a different way. So obviously my interest is this thickness should be captured properly. These walls should be captured properly. That's it. And that's what as simple as even the optimized thin wall resolution and automatic settings has done it. Now so I take one of these completed ones. Okay. No, I'll go in for this one. A bit more different. Now the settings are in the form of, let me not take this one. Okay, I'll take only one option, which is particular thing, which is you can manual specification of minimum gap size. So the guy knows the thicknesses around here, right? These are the small gaps which are present here. So that minimum gap has been specified here manually. If you can also use the second option and select the thickness directly from the geometry. Even that can be done. The second is same for wall thicknesses. So these small walls are very small. You can select the values here, or you can input it manually down here. This value, I don't know whether he has changed it, but it has been given here. Check out how it looks now. To run only, look, wait, make it a bit more different so that it is fast as well. I'll try 3 here, or make course and only the manual wall thicknesses are given. Let's assume that these values have been given by the user. And change no. Let's look how this mesh will come up. The second option. It faster, but let's see how we are here to be running faster. Yeah, it was perfect. It was quite fast. Now let's see the results. Wow. Coarse mesh, definitely it is coarse mesh, but it's trying to ensure that these thickness are captured properly, even the gaps are captured properly. Okay, you can see that is the difference that this particular option can bring in. And finally, now this option itself, if I show you, the option of saying automatic setting. So it is not done by the software, but you want to drive it. Okay, you drive it. So in this case, we have this. If I put a complex option by which I can specify number of cells in the X, Y, and Z direction. The number of cells that I want, I can specify it. There I can add different planes, and say B2 locations, what is the level of or the number of elements that I want. I think I can directly jump onto this now. I can go in here, initial mesh, it is somewhere here. So now take an example. Okay, if I take an example here, can I see the mesh down here? Is it created? No, it is. Load the results. Can it load? No, these are not done. Okay, let's do it later. First, finish the discussion. See here, number we are specifying now. For example, if I take this Z direction, which is along this thickness, I'm saying I have 32 elements, and also visible, I am saying I have 30 elements. So I am fine with having core mesh along the 30 because most the amount of area it is all blank here, nothing around here, so it is fine to have core. I need refined mesh only here. I need refined mesh only along here somewhere, right? So this is the kind of mesh that I need, that I can control from here. So what I do is I give the location of the plane. So between 0.64 some other further values and this one, I'm saying there are 32 cells. The Y direction which is taken Z. But now in terms of Z, we are having a bit more segregation. That is, it is from the that are given here, but I'm selecting a few more points down here. From minus 0.4 to 0.2, create 15 elements. What is that? Let me escape. 2 again. Okay, so what I mean is from minus 4 to 0.2, it could be somewhere here. It's somewhere here, somewhere minus 0.4 could be here to plus 0.2. Somewhere in this region or this plane, okay, between these two walls, I want 15 elements. So that is I'm specifying here. However, from 0.2 to 0.4, I'm happy with 5 elements and giving the change in ratio. So this here, Let me cancel this. Let me mesh this. It might take a little bit more, but I'm okay to wait. You can want to calculate. I just want the mesh. Okay. Frankly, this is a bit more complex. I wish this front end was a bit more easier and to use, but that's how it is. Called as the control plane method, and using this you can control the elements. Let me see how this mesh looks. So this way it has been happen. I would expect the z directional now total number of elements to be 32 and across height, and on because of the refinements that we have given here, especially along this. So I was talking to you. But you can see it is an overlap. It is not an absolute control technique, but it is also overlapping with the other details, and then the thicknesses are captured well. But you can actually control it in this way, wherein we are actually saying number of edges across a certain thickness. Okay, let me show you this one. Let me unsuppress. I thought this suppress. Is it already active in here? It's okay. I thought on this one, and that's the thing which is created of mesh. Let me suppress you and show you how to create it. I'll show you this option later. That the mesh that is created now is not only because of the control plane, but not only because of this, but someone who overruled was this particular local initial mesh. Okay, let me create a mesh with this thing to show how it looks. And now the influence will be only of the control planes. Okay, see how it looks. I know not played too much with mesh, but it's good to know all these things. Most times the local initial mesh is enough, and that can cover most of the scenario. However, be aware of these options and use them appropriately. Let me show you this. Okay, more control planes. Okay, so as simple as this. Now I am to show the exact difference. I think the better way would be I take the automatic settings here. I use the three. I get rid of these two guys. I don't want to use them. Okay, and rely only on this thing. The option is somewhere here. Insert. I think it is somewhere here. Local initial mesh. You can do that. You can set. Okay. Now there is something the dummy component here again. Okay. There are dummy components which have been created here or used. Now in this case, see here there is a component which is created here, local mesh 2. Okay, let me show you if you want to see how it looks. Okay. So we create dummy components which can be used to control the mesh. This is the simple cylindrical body which should encompassing the pin here which is creating the pollutant inside this domain. Okay, let's go back here, local initial mesh. Let me suppress. Hopefully this one is selecting that particular body. Yeah, so this body is selected here. It is nothing but sitting somewhere on here. We have few other detailed controls here like equal automatic settings inside that body. By the way, this is inside the body. Oops, I should have that. Inside the body, and this body is disabled. It no significance apart from controlling the mesh. On more of slider based controls here. So the interaction between solid and fluid, how many cells to have, removing the cells at appropriate locations, you can control this. Arrow channels, if at all there are there, then how to treat them. All these come into picture here. Let me just keep this. Let me keep these at the default things. Hopefully default, right? Yeah. So let's see how this particular mesh looks. I don't know the solve. Again, if I repeat, there are only three controls. One is the initial mesh, second is the local initial mesh using this particular control, and the third one is the control plane technique. That's it. Control plane technique is a bit more intricate. Even I personally don't like it. But this, if you have situations, especially in case where the huge number of holes, huge number of entities to be covered, then control planes are better. However, such cases where at a certain location only you want a refined mesh, then this particular local, just get a component at that thing, display it, use it to control the mesh. That's it. In flow analysis, it is a bit risky to refine the mesh at the global level because we had a lot of elements and it can be complex. A few adaptive techniques as well, that is based on the place where the oops, okay, are you sure? No, finish normally. Okay, let's look almost similar, but ideally if you see here inside this domain where this is present, it is creating a more refined and finer mesh. Obviously this can be controlled further by having more number of elements or details here, and that can do it. Or you can also do automatic setting, go here and have more number of elements. What does this? I think it's fine. 8. Okay. To show you, I'm just triggering this. Let's see how it looks. Mesh. Yeah, I clicked it. Okay. Lesson number 2, which is more of a option oriented things, that is there is nothing much to explain. It is more on how to do it, buttons and clicks. I asked you to go through it before we come to the next session. The case studies or the exercises given inside it are also good. They in a simple ways with some simple different examples. They explain how to use these different options. To explore it, that will give you a good understanding and control on how to tell meshes in flow simulation. Different cases, it could be simple thin components, it could be a wall kind of thing with multiple holes, how to handle it. So all those kind of different cases are over there. Okay, let's see how this looks. I expect it to be refined only at local condition. It is propagating. So irrespective of what I do, as I told you, it has its own intelligence. Irrespective of what I force it, it will ensure appropriate mesh is created at the right locations. But wherever you are telling it to have a refined mesh, it is ensuring it is delivering that kind of mesh as well. So, yeah, I can keep on going testing these different scenarios. Unfortunately, every time I test, it takes a bit of, but the request would be you try these things at your own convenience and test different options. Basically, there are only 3 different options. One is local initial mesh, automatic. Second, control planes. You are creating planes and giving the number of elements between those planes. And one is this one, which is called as local initial mesh. That's it. These are the few. If someone asks you what are the mesh controls in flow simulation, lesson 2, these are the 3 different controls that one can play with. So inside, once you are into those options, you do have many options to run it and try it. Obviously, it's difficult to explain those options, but if you want to experiment and try it, nothing wrong. But for all practical purposes, I would say I am personally comfortable with the local initial mesh. Do a good job. Guys, questions? As well, if you want, you can explore these things. It gives a bit of option to refine the mesh, so you can actually use it to it more. It gets confusing after some time because there are too many options, and ultimately it is, we may not have control in the sense if I change a certain parameter, how is it affecting the results? I have no idea. It is difficult to find out. I think my suggestion, stick to the local initial mesh. That should take you in the right direction. Yeah. Component control. Okay. If you mind, could you show me how to define inlet volume for this case? How have they defined the inlet volume? Let me check. The one which is telling me to show me how to define the inlet volume. Guys, other questions, please ask. Otherwise, we are at the end of this session. Thanks for attending it. Tomorrow we'll start from lesson number 3. If you want to wait and see how I define the inlet volume, please stay back. It's okay. Thanks a lot for attending it. Volume instrument conditions. Let me hide the mesh here. Let me geometry. Let me zoom in here. Poly. Yeah. Can down here. The volume flow has been defined on this one, Ahmed. So we think, but typically in right click, insert volume flow rate and select this particular surface. So the pollutant which is getting created and that disperses into this domain, and we define the inlet volume flow rate on this component.